Hi, this is Michael from Ansoft. In this video, we'll show you how to import a UTexas4 data file into the EnFEM program to perform a slope stability analysis using the strength reduction finite element method. UTexas4 is a 2D limit equilibrium slope stability analysis program developed by Dr. Stephen Wright of Chinook Software. EnFEM is a 2D general-purpose finite element software developed at Ansoft. First, let's take a look at the geometry of the example slope in the UTexas4 program. This example is the second tutorial case provided with UTexas4. A non-circular slip surface search was used to identify the critical slip surface. The analysis results show a safety factor of 0.962. Now let's run EnFEM for the finite element analysis. Open EnFEM, click on File, and select Import. EnFEM supports importing input files from both UTexas4 and ANSlope. Click on Import from UTexas4 and select the tutorial2.pre-input UTexas file. EnFEM will generate a model based on the imported UTexas4 data. From the Pre-Mesh menu, select Auto Mesh Generation. The program will create a mesh for the model and automatically switch from design mode to mesh mode. Now the model is ready for analysis. From the Analysis menu, select Run Analysis. Choose both Initial Soil Stress and Stability (SRM) stages. Click Run to start the analysis. A terminal window will appear, displaying the progress of the computations. Once the analysis is complete, a log file summarizing the results will appear. Users can switch to Result mode to view the analysis output. Click on Plot Contour to display the deformation results. The safety factor of the last converged solution is 0.976, which is close to 0.962 from UTexas4. The slightly higher value is due to default input settings used in the finite element model. A small cohesion value of 72 pounds per square foot is automatically assigned to materials with zero cohesion when EnFEM imports the data file from UTexas4. This small cohesion is added to help ensure convergence in the initial analysis. Let's now change the cohesion back to 0 PSF. Change the cohesion values for both high plasticity clay and sandy gravel to 0 pounds per square foot. Run analyses again. Click on Plot Contour to display the deformation results. The safety factor of the last converged solution is 0.951. This value is slightly lower than 0.962 from UTexas4. Change the group to strain and the variable to PEEQ. PEEQ stands for the equivalent magnitude of plastic strain. The slip surface can be clearly seen in the weak layer and at the toe region. To better visualize the entire slip surface, lower the maximum value to 1 and click Apply. By overlaying the figure with the output from UTexas4 in graphical software such as PowerPoint, we can observe that the slip surfaces predicted by both programs are closely aligned. Switch back to EnFEM. Change the group to deformation and the variable to U magnitude. We can observe that the deformation of the sliding block is not uniform. In the final stage of analysis, the deformation at the toe of the slope is approximately 27 feet, while it is about 8 feet at the top of the slope. This shows that the sliding block does not behave as a rigid body as assumed in limit equilibrium analyses. The maximum deformation ranges from about 27 feet at a safety factor of 0.951 to about 3 feet at a safety factor of 0.884. Engineers might choose to adopt a smaller safety factor based on allowable deformation limits. This example demonstrates how easily a strength reduction finite element method, FEM slope stability analysis, can be performed using EnFEM's import function. In addition to calculating the safety factor, finite element analysis also provides the deformation associated with each safety factor. This allows engineers to select a safety factor based on allowable deformation criteria. Thank you. For more information, please visit ensoftinc.com.